Okay guys, we're going to go over the problem. I know it was kind of quick, but just watch my explanation anyway. You'll learn something. Okay, so this is the same PT diagram we were working on earlier. So let's just again situate ourselves on this diagram. We have three regions: solid, liquid, and vapor. And how I like to think about it is if I stay at a constant pressure, like 1 atmosphere, if I'm at very, very low temperatures, things will freeze, so I'll be in the solid region. If I get hotter, I'll go to liquid, and then the very, very hottest will go to vapor. Okay? So that means then these lines in between are equilibrium between the two phases that they separate. So this line, because it falls in between solid liquid, will be a solid liquid freezing line. This one will be liquid vapor because it divides liquid and vapor. And same thing with this one, solid and vapor. All right. Does anyone know what this point right here is called?
The critical point?
Right, the critical point. Yep. And that represents the end of the boiling curve. So above this point, the liquid and vapors have the same densities, and we can't distinguish them. What about this point right here?
Triple point?
The triple point, yep. And that's when solid, liquid, and vapor are all in equilibrium. So just two other points to notice on this graph. Okay, so now let's characterize path one. Once we have these phases here, it's pretty easy to tell what's going on. We're staying at a constant pressure of 20 spheres, and we're just going from solid to liquid to vapor. Okay. Before I go to the next slide, I have a 3D model. I don't know if I should have showed this. But I have a 3D model of this that's going on. So really there are three variables when we're talking about the state of a substance. So we have pressure and temperature here, but we also have volume. So we can think about a thermodynamic surface that characterizes the pressure, temperature, and volume behavior of all of this. So for pressure and temperature, if we think of this as the 3D surface, this is at a volume slice. So we can think of it as looking on this apparatus, looking at it straight on like that. And if maybe afterwards you guys can see it, if you kind of get at eye level with this, this graph and this projection will look exactly the same. So it's kind of cool. So this is the PT projections. All right, now we want to map this onto our PV diagram. So it's going to be a little bit different. So we're gonna again situate ourselves on this, locate our phases, and how I like to start on these diagrams is remembering that these black curves are all talking about equilibrium. So on this graph, we see that we have these pockets of equilibrium, and we know that that's going to describe behavior of two phases. So we see we have a pocket in here, and this pocket in here will eventually, these two will come together. So this is also a pocket here. So I know that I can't have single phases inside of these. So that leaves three other regions left that will be our pure phases. And if we just, again, think of a constant pressure and kind of rationalize as we're going higher in volume, we expect things with very small volumes, things that are very dense, to be solids. Where you typically think of solids as like sinking in a liquid, being very compact. So we'll have a small specific volume. So it's on the left side. And as we increase the volume, it's like, all right, liquids will be a little bit bigger. And vapors, if we put some gas in this room, will expand to fill the whole room, have a very, very high specific volume. So we have three regions here. And just like how we did it on the last one, that means things in between are equilibriums between the phases that they separate. So this will be the liquid and vapor equilibrium because it's separating liquid and vapor. This one will be solid and vapor because it's right in between them. And then this little slice is solid and liquid equilibrium. Okay, so we also located the critical point on the last one. Where on this graph does the critical point lie? Does anyone know? Any ideas? Perfect, yep. She said right here. Because that's the point that we stop having liquid-vapor equilibrium. We can't tell the difference. So if this is the liquid regime, and this is the vapor, well, up here we don't know what it is. So this point is the critical point. And then where on this is the triple point?
The line between the liquid vapor region and the solid vapor region is the whole line.
This whole line? Yep, exactly. Because at this pressure, we have equilibrium at the solid, liquid, and vapor points, all three phases. Okay. That we don't really, it's just kind of something good to look at. Okay, so this is what we found out. Path 1 goes from solid, liquid to vapor at 20 atmospheres, so it's pretty easy. We just start at 20 in the solid region, and since we've already labeled the phases, we know that this line should just go straight across. All right? So point A is at solid-liquid equilibrium. Good, we've labeled this region, and we know it has to be at 20 atmospheres. So point A better lie on these 2 points here, with the left curve being solid, because it's now the solid phase boundary, and the right point will be liquid because it's at the liquid phase boundary. And then we could just read off the specific volume. Same thing with B, only this is at liquid vapor equilibrium, so the points are right there. All right, and if we just rotate this surface here, this is the PV projection. You can kind of see, here's this liquid vapor envelope, here would be the solid here. Again, you can kind of see if you go down at like the level of that, it'll look exactly like this plot. All right, path 2, back on the PT diagram, we see that this is going to be a constant temperature path going from liquid to vapor. And it's going to hit equilibrium at 2 atmospheres. So if we translate that to here, we know that it has to hit liquid at 2 atmospheres. We also know that liquids are relatively incompressible, so as we're changing the pressure, we don't expect the volume to change very much. So we're just going to follow a constant volume line up to where we started, which was 100. Right, so if we start at 100, going constant volume, and maintaining equilibrium, we see that the path looks like that. Point C we said is at liquid vapor equilibrium, so we can just read off the points. And then to find point D, we have to realize that it's going to act like an ideal gas in this vapor region. So if we start with the ideal gas formula, we have to have this factor of molar mass here because we're dealing with specific volume, which has cubic meters per kilogram, and ideal gas law is typically with a molar volume. Just don't forget to include that. So anyway, starting with gas law, if we take the logarithm of both sides, we see that this actually becomes linear. If we plot log P versus log V, it's kind of like a y equals mx plus b plot with a slope of -1. So all we have to do now is draw from here a line with a slope of -1 until we reach the pressure that point D was, which was 0.02 atmospheres. And then we can just read off the point here for the specific volume. Are there any questions? I suggest you come and look at this. It's really cool to see those different projections.
We have homework 10.